Okay, hello and welcome to 26th class of Physics 2. We are in the studies of electromagnetic theory, as you know, and as I told you, the entire electromagnetic theory is based on the four laws of Maxwell's four laws. The first law of Maxwell is related to the electrostatics, second law is related to magnetostatics, third law is related to the electromagnetics, and fourth law is related to electromagnetic theory. So one by one, each law will be coming into our discussion because based on this law, the equation of electromagnetic wave was done actually based on the third law and fourth law. It was done by Maxwell, and that is the equation which is explaining how any electromagnetic wave, like light wave, radio signal, how it traverses through a medium. Okay, how it traverses through free space, how it traverses through the medium. So all these stories can be unfolded if you know this topic and chapter very carefully. It's a classical idea, so basically it is talking about how based on the basic classical principle of electrostatics, magnetostatics, electromagnetics, and EM theory. So one by one we'll learn them, but this entire study, as I mentioned in my previous video lecture, is based on the studies of vectors. Okay, so vector, mainly vector calculus, vector differentiation part we discussed in my previous video lecture. Most of the things you know. What I intended to do, I actually intended to explain the physical meaning of all these things, because how gradient is taken. You take gradient of a scalar function. Okay, what does it mean physically? It talks about a change of a scalar function. What is directional derivative? It's a change in a specific direction of the scalar function. What is divergence? Divergence means flow of the function. If it is zero, no flow. If it is greater than zero, flowing out. So for example, a positive charge, electric fields are flowing out. If it is negative flow flowing in, that is, suppose I've got a negative charge, electric flow lines of forces are coming in. Okay, so that is the concept of divergence. Divergence means flow. Now these ideas will be very much essential for the application in electrostatics, where we'll talk about the charges, magnetostatics, where we talk about the magnetic poles. So there you'll be talking about lines of forces, that is the direction in the direction tangent to the lines of force. Obviously gives you the direction of the applied force. All these things you know from old studies. So there all these ideas will be connected. They are electric line, magnetic line of forces will flow out or in, all these things will happen. So there you have to calculate divergences. Now you should try to keep it in mind, divergence means flow. Okay, so divergence means the flow of the electric and magnetic field. And curl means rotation. Okay, if curl is zero, curl mathematically speaking you have to resolve a determinant, but physically speaking, if you take curl of a vector is zero, that means it cannot rotate. And if it is non-zero, it is rotational, like velocity vector. Now I have shown you the example of Amphan, the wind cyclone. It has got a rotational tendency. Curl will be non-zero, like that. So this is something from the differentiation part, change in the vectorial part or change in the scalar part. Now today we'll mainly concentrate on the integral part, okay, of the study. Okay, so this is the basic concept of vectors. This is the concept of the divergence, sorry, gradient. Temperature is a scalar quantity and it changes, as you can see there. Okay, this is, again, if you heat a rod at one end, and okay, there is a gradient of temperature. It's a scalar. This is the sunlight. Okay, there is a gradient of the ray sunlight. Okay, okay, this is how you take gradient. This is the concept of directional derivative. You dot product multiply the dot unit vector in that direction, and this is the animation that shows that gradient means you take the slope. A classical coordinate geometry slope means gradient of the curve. Okay, so in a definite direction it is called directional derivative. Now divergence, as I told you, flowing out, flowing in, greater than zero is going out, less than zero is coming in, and non-zero means no field. And it's a beautiful picture. It is available in my previous video lecture also. You can see there. Okay, that is the, you can see there lines of forces are going out. Okay, that is the divergence of the vector. You can see there. Now Laplacian operator came into business. If you take divergence of a gradient of a scalar function, you get the del square operator. It is called Laplacian operator. Okay, And another these are the few examples I discussed. Now this is a curl. Okay, curl means rotation, rotation of the vector. Okay, okay, you can see the rotation of the vector. The wind is getting rotated. Okay, okay, you can see there. This is the curl. This is the rotation. So the velocity vector of the storm. Okay, should as is curl. If you take the curl of that velocity vector, it will be non-zero. Okay, so this is how do you resolve it. Calculate curl by resolving determinant. Okay, divergence of curl of a vector is zero. Curl of gradient of a vector is zero. Okay, now talking about the vector integration, I will actually tell you how this vector integration could be calculated, how it could be done. Okay, let me tell you let me tell you with an example. Okay, let me show you the calculation directly. One person is here. He wants to walk along this one-dimensional path. Okay, so this is the uh, length vector r is there. So if the person walks in this direction by applying a force, suppose he is applying a force F to work in that direction. So amount of work done in moving through this length is F dot dr1. Amount of work done in moving through this much of length is F dot dr2. Amount of moving work done in moving through this much of length F dot dr3. So as he is working on, okay, so he is keeping on doing work. So here F dot dr4. So here amount of work done is F dot dr5, and similarly if you keep on doing it, it is F dot dr1. So automatic question comes in, what is the total work done moving through this length? Suppose the person is coming from the point A to the some other point, say B. So total work done will be summation of all these. So if I call it W, okay, total work done will be summation of all these individual work done. So it is like W1, this is like W2, W3, W4, W5, and so on up to say Wn. So total work done means you add individual Ws. Okay, because total means you have to keep on adding them. So now, so basically what you are doing, you are adding this part, 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 you are adding work done in this part, work done in moving this part, like that. So what you are doing, so if you are doing this summation means you are adding, okay, you are actually, okay, you are doing this summation means what you are doing, this path starting from the point A and going ending at the point B, you see this path is a continuous path. So if you do this summation, you are doing a summation over a continuous path. And you know, summation over a continuous path is called an integration. So we can express this as an integration. This is nothing but it can be written as an integration over FDR. And it will go run from the point A to the point B. Okay. So total work done would be F dot dr, and it will run from the point A to the point B. Okay, because it's a continuous path, you can the summation over a continuous path is called an integration. So because what you are doing, okay, you are as you are moving from A to B, suppose this is x equal to 0, and suppose this is x equal to say L. So what he is doing, A means x equal to 0, the person is reaching at x equal to L. So along a length element L, okay, as the person moves, he does this much of amount of work. And this is nothing but summation. What I am doing, I'm doing small work. Okay, and that works are done as a person is walking over a linear path. So this is what I am doing. I am adding over a line. Integration in summation, so I am adding over a line. So that's why this type of integral, okay, what you are doing, this integral is nothing but I am doing a line integral. So line integral means you do add, you do integrate over a line. Okay. So line integral means here I am doing a line integral. I am integrating over a line. That's why it is called a line integral. Same thing I can do for this is a linear discussion for a circular path. Suppose this is a circle, and I suppose they at the center. Suppose a force, a body is here. Okay, a matter is moving here, and I am applying a tangential force in this direction. So the body is suppose moving along this path. So it is kept on moving like this. Okay, it is moving like this way. So the tangential force cannot allow it. Suppose it is under attractive force here. Suppose Coulomb force is there plus Q charge, and this is minus Q charge, and the Coulomb force will allow it to move along this path. Okay, because of this nature. Okay, so ultimately what it is doing, as it is moving from here to there, it is as the charge was initially here, maybe some point A. Suppose it is coming to this position and traversing a length dr1. Okay, again as it is moving from here to there, you are doing some work f dr1. As it will come here, you will do a bit of more work f dr2, considering f is the applied force. Okay. Now if you are doing here, coming here, again you will do a bit of more work f dr3. This is dr2, this is dr3, and so on. If this is dr4, this is f dot dr1. Okay, f dot dr2. Next one is f dot dr3. Next one is f dot dr4, and so on. So if you keep on moving along this path, okay, you have to. Okay, you have to. There will be so many f's coming. Say at one stage, see this will be f dot drn. Okay, if you keep on adding them. So again, what you are doing, if you what is the total work done? Total means total work done. If I have to calculate, you have to calculate total work done. What I will be doing, I will be adding these individual work done. This plus this plus this plus this. I will be adding this individual work done. So what you are doing, adding this individual means you are actually working over the circular path. Okay. So again, you are working over a circular path, and we can write down this integration as f dot dr over this circular path. Now this is also called a line integral. So line integral means this is a line integral over a closed loop. Okay. So line integral may be like this much. If somebody walks, it may be like this much. Okay. If somebody walks, suppose a person is walking from this point to this point. If he walks in this path, and if the amount of work done, that is also is integration from A to B. So this is an expression of the line integral over the linear path. And if somebody moves also in a circular path also, from here to here to here to here, so the amount of work done is also a line integral. Okay, it's still because it is moving in a loop, you may consider it is moving over the closed loop C. This is also line integral. So line integral means basically it is giving you the work done, total work done kind of thing. Okay, that is giving the information. Integration over a line, integration over a path. Now another beautiful concept is the concept of surface integral. Now surface integrals are true when you consider a surface. Suppose I consider a sphere. Now on the surface, I could choose any surface area, say ds. Suppose unit vector to the surface is a gap. Now let us take a practical example. Suppose I have got a charge plus q here, and I have got a unit charge q equal to 1 here. So along this direction, the electric force will act, the electric field will act. So this is called electric line of force, it is coming out. So now electric line of force is perpendicular to the vector that is along the radius. Now if I consider a surface area ds is basically magnitude of ds and the normal to the surface. So total electric line of force that is coming out through this entire surface area will be basically, if for this one I call it say EDS, suppose for the one it is EDS, it will be E dot ds, that is the, okay, because one line of force coming out is E. So total electric line of force coming out through this surface area ds, okay, you have to do a surface, you have to, this has to be, okay, it is basically E dot ds. E is the line of force. So if I could define here, E is the line of force coming through a point. So line of force coming out through an elementary area ds is basically E dot ds. If I choose ds1, it will be E dot ds1. So if I choose any other surface area, say ds2, so total number of line of force that is coming out through this surface area, we may call it E dot ds2. So if I consider any other surface area, say ds3, green vector is n cap. So total line of force that is coming out, okay, E dot ds3, ds4, total line of force coming out is E dot ds4. So basically total line of force coming out, total line of lines of forces coming out is basically summation of all these E dot ds. Now if you consider the entire surface, okay, for the entire surface, it is an integration E dot ds over the entire surface. So then it is called a surface integral E dot ds. Okay. So this is the concept of E dot ds. It talks about net flux coming out of the surface. This is called the concept of volume and surface integral. So with this in mind, just let me get back to the PowerPoint, okay, so that you can connect yourself. If you look at the PowerPoint a bit, if we see, now look here. Now if you look here, this is the case of a line integral f dot dr. Okay, the same thing I shown you. Okay, the work done is being shown here. Okay, you can see there f dot dr. The force is there, the body is moving, and that is the work done. And you can see the right hand side line also. Okay. Now this is how you see the whale will fall down. Okay, it is another beautiful example. Okay. Now again, let me how the whale will fall down. Okay, let me again show you. It is another problem of line integral. It's a beautiful problem. You see, if you look here, some elementary areas there. Okay, here this much of length. We may call some amount of length say dr1. Okay, so amount of work done. So this we will describe as some amount of length say dr2. This we will describe by some amount of length maybe dr3. So as the body is falling down, so obviously total work done, if F is the force experienced, so total work done basically summation of this thing, that is F dr1, F dot dr1 plus F dot dr2 plus F dot dr3 So basically, simply say you can add the contribution of f dot dr 4. You can add this contribution of f dot dr 5 like that. So finally, what you are doing, you are adding this individual work done. So these becomes, and what you have to do. So what is the total work done? There is a line integral. If this is the point A, if this is the point B, if this is the point, then total work done is basically f dot dr. Okay. Okay. It is integrated from the point A to the B. So this will be in line integral you'll be doing to know how much amount of energy work you'll be doing as the whale falling down. Okay. So these are the way you can do it. Okay. Now these are some more examples of calculation of line integral. You can see there more examples are here. Look at the line integral example. Now surface integral I just told you. So we have taken a surface there. The net work done by the total flux coming out is f dot ds. Okay. Now come to the case of volume integral. Now again let me show you. Okay, the case of volume integral. You can see volume integral means basically summation over some small volume elements. Okay. So let me again show you in reality how it is done. So volume integral is like this much. Suppose I consider a small volume element dV. Now if it suppose this volume element is making a big block, of volume V. So these are the small. So basically, how this total big volume V is made of? By suppose this is dV1, dV1. Suppose side by that there is another volume element you can define. Suppose this is dV2. Now this is maybe dV3. This will be dV4. Like this. Okay, you can keep on adding. This will be dV5. So total volume is basically dV1, dV2, dV3, so on up to dV5. And if I, so basically this gives you the total volume because it's a continuity is there. It's a continuous volume is the element is there. And you're adding all the individual volume elements. So again now, so what you are getting, you can express this as an integration over the volume element V. Suppose I have to calculate the mass. The mass of the unit volume may be rho. So basically, for the mass calculation, it will be rho dV. Suppose that will give you the full mass. So volume integral is a simple. You have to integrate it over the full volume. Okay. So now let's. Okay. So how this is how it is done. Surface integral and volume integral, as you can see there, they are connected. Surface integral means total flux coming out, and volume integral is the total of the. Okay. Suppose any scalar variable, like in this case density or mass, temperature, the total you calculate. Okay. Now the connection between surface and volume integral is given by Gauss's divergence theorem. It tells us, I give you, again I show you. Okay, if you realize. Okay. Suppose I have got a surface area. Suppose I have got a sphere. At the center of it, I have got a positive charge Q, and the total surface area is A, and this is electric lines of forces coming out. Now, total electric line of forces coming out. You see, total electric line of forces coming. That means I am considering all the electric line of forces are coming out. So total electric line of forces are coming out is the surface integral. And force is this flowing out according to the vectors, is expressed by divergence. So basically that net flow is basically divergence over the full volume element. Now this is called the Gauss's divergence theorem. There is volume integral, divergence of volume integral is connected with the surface integral. So, this is called the connection between volume integral and surface integral. Volume integral and surface integrals are connected by this formula. Now this equation is a very famous equation. We'll use it time and again. This is called Gauss's. This is called Gauss's divergence theorem. GAUSS. Okay, in electrostatics also you'll get Gauss's another theorem. Okay, that is called Gauss's law of electrostatics. So don't mix it. Okay. Gauss's divergence theorem is connected with connecting volume integral with the surface integral. Okay, done. Now another popular idea. Okay, another popular idea is if let me get back to the PPT again. So this is the connection between surface integral and volume integral, as you can see there. Now another popular idea is to connect line integral with the surface integral. Okay, if we see how I am doing. Okay, connection of line integral surface line like this much. So this is total surface area. Now n cap is the normal, ds is the total any surface element. So that ds vector is like ds. If I integrate it, totally I'll get the full surface area like this much. Now if somebody suppose walking along this path, again amount of work done is over this incremental length to be fd or dot dr1. So as the person will be walking along so somebody is walking along this path. So total work done will be equal to f dot dr1 dr actually, because I have to add on all these individual work f dot dr2 as I have shown you a few minutes back. In this case, say dr3. So amount of work done will be like f dot dr3. In this case, maybe drn. So amount of work done will be f dot dr1. And so if you add all the same, you get the total work done f dot dr. If I integrate it over the full circular path, so it will be like closed loop line integral. Now this will be equal to the total number of what the person is doing. He is actually rotating over the path. So that rotation is taken care of by the term curl. So this is equal to curl of the vector over this closed surface, because that is taking care of the rotation term. Okay, so this is famous. Okay, Stokes law. Now I have Stokes law converges to the Green's theorem when we consider a 2D surface. Okay, not a 3D surface. Now let me get back to the PowerPoint and realize it. It's so funny, so interesting, and so good. You can see there the connection between the line integral and surface integral there. You can see the connection on the screen. Somebody is actually working on and how it is connected. I hope I have explained it properly in front of you. Okay. And this is the famous Stokes theorem. Okay, you see the lines of forces are coming out and they are connected by this. So Stokes theorem is there and divergence theorem is there. Two very good. Divergence theorem connects line integral with this volume integral, and Stokes theorem connects line integral. Sorry, divergence theorem connects surface integral with the volume integral, and Stokes theorem connect line integral with the surface integral. I have explained you. Divergence theorem tells us that is total surface integral is total flux coming out equal to the total flow across about from the volume. Okay, and Stokes theorem means total work done equal to the number of rotations you carry out. Okay, now this converges to the Green's theorem. Okay, in 2D. Okay, when I consider 2D surface. Now this is a very popular and simple example. I think I have to do it for you. This is very even without doing, I can tell you this is del square V have to take.
So if del square means double derivative, that is 2x will give you 2, and double derivative of y square is basically, it will also give you 2, okay? And next third one is going to give you 0. So the answer will be how much? Answer will be 0, okay? So it is satisfying Laplace's equation. Now here I conclude my discussions on integrals, vector integrals, line integral, which is talking about the work done kind of thing. When you get work done over a line when somebody moves, the surface integral means total flux coming out, and volume integral means total volume integers. Line integral, physically meaning line integral and volume integral are connected. Surface integral connected by Stokes theorem. Line integral and volume integral and surface integral are connected by the divergence theorem of Gauss. Stokes theorem states that is total amount of work done over a circular particle, the total number of rotations done from the across the surface area, and divergence theorem, Gauss's divergence theorem tells total flow of the field, total electric flux to be, in case of electrostatics, you will see it, total flux coming out equal to the total flow of the field across the entire body. So this has been our discussions about both vector calculus, that is both vector calculus and the vector differentiation part in the last earlier video lecture, and today I discuss about the vector integral. So here I conclude, and we'll now next day honors we'll try to apply them for electrostatics. Thank you. Thanks for your question.